Hi there, welcome to your lesson on the sums of arithmetic and geometric series. So today we're going to look at calculating the sums of arithmetic sequences and also the sums of geometric sequences. So we're going to see a few new formulas to add to our list of formulas. Let's begin with a little flashback. Looking back, we looked at something called sigma notation a few lessons ago. So again, this is the Greek letter sigma. It is also called the summation sign, and it means we're going to do a sum. For example, here we have this symbol means give me the sum of I with I values going from 1 to 7. So you put 1 in there plus, then you put 2 in there plus, put 3 in there, and so on until you get to 7, and you'd add all those up. That's what that symbol means. Same thing for the bottom example here. We have the sum of this expression with n values of 1, 2, 3, 4, all the way up to 5 plugged in here. So plug those n values in and then add all those things up. That is what that symbol means. Okay, we also talked about we can have a sequence, but as soon as you write the sequence with a sum of all the terms, it's called a series. So this series could be written with sigma notation, n value of 1, 2, 3, because we have 3 terms here, and there's our rule for that series or sequence, so that's our sum. We have this one, produces these terms, then written as a sum of terms is called a series, and we can write the sigma notation for that as well. All right, here's a couple more. A couple things that occur often with these. We have this one here. We can see k values of 2 all the way to 100. Obviously, you don't want to put in 2, 3, 4, 5. If you had to substitute all those values of k in here, you'd end up with a giant string of things being added up. So sometimes you'll see it noted like this. So if you put a 2 in there, it gives us that. If you put a 3 in there, it gives us that. Then I put plus, dot, 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 ellipses, plus, and then I put the last term. So if I put 100 in here, I get this. I can write it out like that. Of course, I can't find the sum like that, but we'll look at some formulas that help us with this today. Another example here, sometimes you'll see also sigma going to infinity. So here we have n equals 0 through infinity. So obviously you cannot keep putting in n values in here forever, right? You could put 0 in there, and then 1, and then 2 and 3, but you're not going to go all the way to infinity. So in that case, you can just write the first term plus, put in a 1 in there, get the second term plus, dot, 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 goes to infinity. Leave it like that. Again, we'll see some formulas that may help us with things like this today. Okay, so next, if you want more practice with summation symbols and sigma and all that, here's 4 problems. You can pause the video and try some of these just to remind yourself or make sure you understand this skill. These answers will not be shown, however. Okay, now to continue with this lesson, let's look back on the history of math for a little bit. We have this man here. His name is Carl Friedrich Gauss. He lived between these years, and he is often called the Prince of Mathematicians. He contributed amazingly to number theory, algebra, statistics, analysis, differential geometry, electrostatics, astronomy, optics, so much more. He has a method for finding the sum of consecutive numbers. So there's a story. This may be true or not. We're not sure. It's like a legend. Okay, the story is that when he was a young boy, his teacher asked him the class to add up the numbers from 1 to 100. The teacher expected this activity to keep the class quiet for some time. And so he was amazed when Gauss put up his hand and gave the answer 5050 almost immediately. So how did he do it? This is Gauss, by the way, on the old German Deutschmark note. That's how famous he is in Germany. Very famous mathematician and scientist. Okay, so here's how he did it. His technique was, okay, I have to look at these numbers from 1 to 100 and do the sum of those. He basically said, I can pair these numbers off. So for example, 1 and 100 can be paired off, and we get 101 when you add those. Or 2 and 99 can be paired off, and you get 101 as well. And then 3 and 98 also makes 101. Basically, all the pairs of like first and last number, then the next one, they all add up to 101. So now it's just a matter of saying, well, how many of these pairs do we have? Because if we said, for example, we have 10 of those pairs, you can just multiply that by 101, because each pair has that sum, right? But basically, he looks at it this way. This is the first term. This is the last term. So you can add the first and last term, right? Because those give you 101. So if you know the first and last, you're good to go. And then you multiply by the number of pairs there are. And the number of pairs can be determined by saying how many terms in the sequence, which is n. In this case, we have 100 terms in the sequence. n divided by 2, because there are half as many pairs as things in the sequence, right? Because we're pairing them off. So that's our formula, and that's how he came up with it. Let's use that one. So let's take some notes. Now on your notes page, we're going to add the two key formulas for an arithmetic series. So here's how it goes. We begin with this formula that we just figured out. And from there, we look at that and we say, okay, to use this formula, we need u1 and we need un as well. Sometimes we don't know the last term in this sequence that we want to find the sum for. So why don't we go to that un, and we know there's a general rule for u sub n, and the rule is that, right? That's our general arithmetic formula. So why don't we substitute this with this whole thing here? So notice this formula that we just came up with, and this in blue has been replaced by this un formula. So now these two u1s can combine, and we have 2u1 and then n minus 1 times d. So these are the two common formulas for a sum of an arithmetic series. There's this one, and there's this one. Both of these are in your formula booklet. Please write them down on your page. Let me go back in time for a second. We're saying these are formulas for arithmetic series, and that's exactly what this is, right? This is an arithmetic sequence because we're going up by the same number every time, up by 1, up by 1, up by 1. So the common difference is 1, right? So I just want to verify that this is an arithmetic series, right? So there's our two formulas. Make sure you have both this one and this one written down. And now let's look at this example that's given on your page. We are told the first three terms of an arithmetic sequence are this. Let's confirm it's arithmetic. Okay, down by 8, down by 8. Great, it is. Common difference of negative 8. It says find the sum of the first 80. So now, if we wanted to use this first formula, well, we know the first term, but we don't know the last term, which is the 80th term. So again, looking at this problem, we have to choose which formula is better. Well, in this case, since we don't know the 80th term, we could begin by using the UN rule and finding the 80th term, or we can just jump straight to the second formula, which has the UN rule incorporated in it, right? And then use that formula to find the answer for the sum. So let's try that. Let's use the second formula. We have number of terms, 80, divided by 2. 2 times u1. u1 is 23, so 2 times 23, plus n minus 1, so 80 minus 1, and times the common difference of negative 8. So that, calculating all that, should give you the sum of those first 80 terms, and it is this number here. It might be strange that's a negative number, but you can see this common difference is negative 8. So these numbers are shrinking. So if you continue this sequence forever, very soon, actually the next term would be a negative number, and then it would be a growing negative number. That's why our sum of all those terms is a big negative number. Okay, here's another example. This may or may not be on your notes page, so let's try it on a separate page maybe. Let's see if you can find the sum of this one. Okay, this one's a little bit different. This time, let's begin with the general rule, because the problem in this one is we don't know how many terms this is. We know the u1 term, we know the last term un, but we don't know how many terms that is. Like, it doesn't tell us that that's, I don't know, 10, 15, 20 terms in this sequence. We don't know. So let's use the general rule and figure out how many terms we have. Plugging in 81, that last term, and here's our u1 value, n minus 1 times d. The common difference is 4. Solve this for n. N is the only variable, right? Solve for n, and we have n equals 22. So that tells us that 81 is the 22nd term. So now we know we're looking for the sum of 22 terms. So here's our formula. In this case, we can use this one, the simple formula, because we do know the first term and the last term. We know the 81, right? So now we know there's 22 terms divided by 2, first term, last term. Remember, these two are a pair, they make a sum, and every other pair will have the same sum. So how many pairs do we have? Well, 22 by 2, there's going to be 11 pairs, and our sum in total is this value here. Okay, now here's another one, also not on your page perhaps, but let's take a look. So find the n value, or sum of the first, let's see, write an expression. Oh, write an expression first for the sum. So the expression can look like this. We use the sum rule. Again, we use the bigger formula because we didn't know the final term in this series. So we wrote a rule there, a general rule in terms of n. We had to use the big formula because otherwise we'd have a un there. So we write the formula, and now, hence, find the value of n for which the sum is equal to 0. So using this sequence, at some point the sum will be 0, right? Because these numbers are going down, 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 and they'll become negative numbers. So eventually you'll have a certain set of numbers where you add all the positives and then all the negatives, and then they just make 0. So we're trying to figure out when does that occur. So we're going to use the equation for the sum that we just made up, and we're going to say, well, when does the sum, because this represents the sum, when does that equal 0? Now we have this quadratic, which we can factor out 2n here. And if you remember how to solve quadratics, we set the first term equal to 0 and the second term equal to 0, and you get 2 answers. So our answer must be 33. When we have 33 of these terms, we will have a sum of 0. Great question. That's a really good one. Let's now look at geometric series. We just did arithmetic, so let's do geometric now. The rule for these comes from this place. Let's say we had term number 1. Okay, and term number 1 is u1. Term 2 is u1 times r. In a geometric sequence, right, we multiply u1 by r to get the next term. Term number 3 is u1 times r squared, because we're multiplying by r twice to get from u1. And then term number 4, we're doing 1, 2, 3 times r, so r cubed to get term 4, and so on, until you get to term n, which looks like this. Now, we could say that we're going to multiply this side by r, so therefore we'll multiply all these by r as well. So look, I took all those, and each piece has been multiplied by r. And now we have this system of equations. We can subtract one from the other. So notice that these two here are identical, and these two are identical, and all the way to the end, these two are identical also. So if I did this bottom equation minus the top equation, all these things would cancel because you're subtracting them away. And all that would be left is this u1 and this last term here. So we would be left with negative u1 because we're doing this minus that. So this equation minus this one, so it's negative u1, and then this minus 0, so that remains here as a positive. This is a little tricky, and your algebra has to be pretty strong to understand what I'm doing here, but I'm just showing you where the rule came from. This can simplify into this if you move the u1 here. And then let's see what happened here. Factored out a u1 on this side, and on this side we factor out s sub n, and finally you can now divide by r minus 1 on this side, and it's here. So we've created a formula for the sum of n terms. So this is where the formula for geometric series comes from. So we saw the arithmetic, now we're looking at geometric. So let's write that formula down on our page. It says the sum of the first n terms in a geometric series is given by this formula, the one we just got. Or sometimes you'll see it written with this part, see how it's been written backwards, and this part also backwards. These formulas are interchangeable. Either one can be used anytime. The important thing to remember is r cannot be equal to 1 to use this formula. Because if r is equal to 1, it's not really a geometric sequence because the values are not changing. For example, if our first term was 10, and we were multiplying by 1, next term would be 10. Multiply by 1 again, 10 again. That's not really a geometric sequence, so this formula will not work in that case. Okay, here's the example we have on your page. We have we're talking about sums, so we have a sigma symbol here, and here's our geometric sequence, right? You remember a geometric rule looks like this, the general rule, and we can see those pieces here. So for example, u1 is going to be this number here, 6, and then we multiply by r, right? So here's our r value, negative 2, and then we see n minus 1, or I minus 1 in this case, because we're using I here for the sigma. So we're looking for a sum of the first 8, right? Because 1 through 8. So if you did it step by step, you would do first term, next term, right? The first term is 6, because we see u1. Then we multiply by that negative 2, we get negative 12. Then multiply this by negative 2, we get 24. And you could write that out all the way to term number 8, but we can also use the formula we just figured out. So let's confirm that the formula works. So our formula tells us we're going to put the u1 value here. Then we're going to do, I'm using this one, 1 minus ratio to the nth power. So 1 minus negative 2 to the 8th power. And on the bottom we have 1 minus, again, the ratio, negative 2. So that, you have to be very comfortable punching that in your calculator. So do you know how to do that on your calculator? Let me get mine ready, I'll show you. They're ready here, so I'm going to punch in a fraction. First, to punch a fraction, you press alpha, y equals, select number 1, which is that n over d, and then you have a fraction. And then you just enter everything exactly how you see it. So 6, and so on and so on. But my video is running out of time, so give that a try. the answer should be this. Hopefully you got that right. There's a second video with a bunch of problems. Let's do that.